All right, this is the start of Unit 2. The first three chapters are linked together very nicely in this unit. We'll start with plate tectonics, which is this chapter 7, and then chapter 8 and 9 will be earthquakes and volcanoes, which is basically a result of um, continental plates and ocean plates drifting and colliding with one another. And then the last two chapters in this unit will be Introduction to Astronomy and the Physics of Light. All right, so this chapter, chapter 7, is on plate tectonics with the title A Scientific Revolution Unfolds. All right, so this all started back with Alfred Wegener, who first proposed this hypothesis in 1915. He published something called The Origin of Continents and the Ocean, where he first put forth the continental drift hypothesis. So he hypothesized that a supercontinent called Pangaea began breaking apart about 200 million years ago. So continents drifted to their present positions, and also continents broke through the ocean's crust. So that sounds pretty complicated, and you might think in 1915, how was he able to prove any of this? Well, he wasn't. There's going to be a demonstration video on coffee cans, believe it or not, and I'll talk about the differences between hypotheses, theories in this demonstration video. But just understand that he had no real way of proving this, so it was just an hypothesis or an educated guess as to how the continents and oceans ended up being located where they are presently located. All right, so here's a picture of what Wegener described as Pangaea, redrawn from his book in 1912. So the drawing is on the bottom of what he thought, and then the picture on top is just a color-coded version of the same thing, indicating where the current continents or the current names of current continents in today's world. All right, so you can see that he hypothesized that most of everything was connected together at some point 200 million years ago. All right, so how did he come up with this hypothesis? So here was some evidence that Wegener used. So it looks like that the eastern side of South America fits together well with the western side of Africa. He also had some evidence that fossils in South America match some of the same fossils that were found in Africa. So this should suggest that at one point South America and Africa were connected if the same fossils were found in both regions. Rock types and structures also matched, and some of the ancient climates seem to be the same as well, matching up between South America and Africa. So just some examples, some fossils that were found on different continents. You have Mesosaurus, which is this big alligator-like dinosaur swimming creature that was found both in Africa and South America. You also have Lystrosaurus and a plant called Glossopteris found on multiple different continents, suggesting that at one point all of the continents were connected together landmass-wise. Some people rejected this drift hypothesis mainly because Wegener wasn't able to provide a physical process or mechanism for this to happen. And that's just a picture of him shown waiting out the Arctic winter in Greenland, where he was making a 1,200 kilometer, so not a very short trek across the widest part of that island's ice sheet. As we know today, it's its glacier. All right, so there is a new theory, and this is the prevailing theory of today. And notice we're not saying it's a law yet, we're saying it's just a theory, but this is more encompassing than the continental drift hypothesis. So this is associated with Earth's rigid outer shell called the lithosphere. And it consists of several plates. Now these plates are moving slowly, and the largest of all the plates is the Pacific plate, below the Pacific Ocean. And most of these plates are actually below the ocean as well. All right, so this is a picture of Earth's lithospheric plates. So you can see there's a North American plate, the South American plate, African plate. They basically name them after continents and oceans. All right, so one important aspect of this theory is to understand a few layers of the Earth. So we know the lithosphere, that's the outermost layer. The layer below that is the asthenosphere. This layer, being closer to the outer and inner core of the Earth, it is a hotter location than the lithosphere. So since this asthenosphere is made out of different rocks, metals, materials like that, they're a little closer to becoming liquid. So they're near the melting temperature of these rocks. So it allows the layer above the asthenosphere, this lithosphere, to move. You can kind of think about it as if the asthenosphere was, let's say, water, for an extreme example. Anything floating on top of that water could move in, whatever direction on top of the water surface. It's the same basic idea here. So the asthenosphere sort of acts like a liquid that the lithosphere sits on top of, allowing that lithosphere to move. So this motion is very slow. It's not fast at all, but there is some motion of the lithosphere, and that's what we're describing as a continental plate or an ocean plate. Now, there's three types of plate boundaries that you need to be aware of. The three types are divergent plate, convergent plate, and transform plate, and I'll go through the three of those plates at this time. So the first plate, the divergent plate. So we call these constructive margins. So this is where two of the plates are moving apart. So mantle material below the lithosphere upwells to create a new seafloor. So this typically happens between ocean plates. So what we have is we have ocean ridges, which are basically just mountains under the ocean, and the seafloor spread apart. So these oceanic ridges develop along well-developed boundaries. Along ridges, seafloor spreading creates a new seafloor, and the continental rifts form as these two plates spread apart. So I think the picture of this is pretty obvious. So you have liquid metal, or you can think of it as magma from one of the earlier chapters, upswelling between the plate. So when you have this material going up through the boundary, that's going to create these two things to spread apart. So when we have plates colliding with one another, we have a convergent plate boundary. So when this happens, an ocean transforms and lithosphere is subducted into the mantle. So when we have oceanic and continental convergence, so this is when an ocean plate and a continental plate come together, the denser oceanic plate sinks into the asthenosphere. So we have part of the lithosphere in that region sinking down underneath the asthenosphere. So pockets of magma develop and then rise up at that location. So this is where we end up seeing volcanoes forming on Earth. So some example of locations would be the Andes Mountains, Cascades Mountains, and the Sierra Nevada system in California. So here's a picture of what I was just describing. You have the ocean plate subducting or going underneath the continental plate, and when that happens, it forces magma and lava to come up through the asthenosphere into the lithosphere, and then eventually forming volcanoes near the Earth's surface. All right, now when you have an oceanic to oceanic convergence, so when two oceanic plates are converging, one simply distends below the other, and again, volcanoes are forming, but this time the volcanoes are forming in the ocean. So this is where you would have volcanic island arcs forming as volcanoes emerge from the sea. So some examples would be the Aleutian Islands, the Mariana, and Tonga Islands. And this is just a picture of island regions in the Pacific near Alaska. So you can see that this is an area of an oceanic convergence where you're having island chains forming and where you have volcanoes being formed in these regions. All right, when you have continental convergence, so two continental plates coming together, one plate is subducted underneath the other, and this can produce new mountain ranges such as the Himalayas. So just another example of a continent converging. So you're always going to have some uprising of material, and it's typically in the form of volcanoes or mountains. All right, the third type is a transform fault boundaries, and this is where the plates don't actually move above or below one another, but it's where they slip side to side. So it's probably best seen in this picture here. So this is an example of a divergent boundary being next to a transform boundary. So actually, this is a plate here, and this is a plate here, and they're moving in this direction. It's very hard to see, but there's an arrow moving to the left here and an arrow moving to the right. So these are two plates slipping side by side. So this is what happens off the coast of California in certain regions. All right, changing plates and plate boundaries. So plates and boundaries migrate and are created and destroyed. So in the breakup of Pangaea, you had the continent that we know today as South America moving westward, and the continent we know as Africa were moving eastward. So when those plates are moving apart, you end up forming new regions, and when those two regions moved, we formed a new ocean basin, which we're now calling the Atlantic Ocean. And this is just a picture showing you sort of step-by-step pictures of what happens. And you'll notice this takes a very long time to happen. So we go from 200 to 150 million years ago, from 90, 50, 20, and then finally to present day. So even 20 million years ago, the Earth looked very similar to what it looks like today. We're talking about continental plates moving maybe 2 centimeters per year. So we're not talking about these things moving very rapidly at all. But there's more evidence for this theory of plate tectonics than there was for the continental drift hypothesis.